go.
For starters, we were given a table of molecules that were synthesized in Dr. Charage's lab and were informed that our molecule was one of these. We immediately focused on the IR spectrum and trying to figure out what the peaks referred to. Immediately, we found a rather noticeable peak around the 3,300 to 3,600 wave number range. By then referring to a table of characteristic IR absorptions for different functional groups, we found two bonds that could create this peak in IR, an NH bond and an OH bond. These have wave number ranges of 3,300 to 3,500 and 3,200 to 3,600 respectively. As a result, we couldn't definitively say that it was one bond or the other. We moved on to the next peak and identified it as a CH bond, with a range of about 2,850 to 3,000, exactly what was expected for a CH bond. The next peak chosen was in the 1,700 to 1,750 range, which most closely matched with a carbon double bonded to an oxygen. This has a range of about 1,650 to 1,820.
The next few peaks were a little harder to identify, and so we began to look at the structures of the molecules provided. Having found a distinct peak at the mysterious OH and NH bond area, we ruled out the first half of the table, the reactants, because they all didn't include any OH or NH bonds. When we saw the molecule structures, however, we noticed that because they were all derivatives of toluene and benzaldehyde, all of the molecules displayed carbon rings, and so we were able to identify the peak in the IR spectrum around 1550 to 1600 as a carbon double bonded to a carbon. When we saw the different molecules, we noticed that two molecules, 3-nitrobenzaldehyde and 4-nitrobenzaldehyde, had, I don't know how to say that, which we realized were highly electronegative and so would readily attract a hydrogen to itself. So if contaminants were present during the testing, an OH bond would be visible. We decided to then work with these two molecules. In addition, the presence of a CN bond would explain the last peak on the IR spectrum around the 1050 to 1380 range.
We then looked at our NMR spectrum. It had a clear peak near 10 parts per million, and then what looked like a multiplet, then a triplet, followed by two singlets. The solvent was determined to be chloroform D because the peak appeared at about 7.245 parts per million, which was practically that for chloroform D, or 7.26. The singlet around 10 was left as a singlet. The triplet near 7.75 parts per million was left as such, and the last singlet around 1.57 parts per million was also left alone. The multiplet was split into a singlet and then two doublets, because the peak around 8.72 parts per million seemed to be separate from the surrounding peaks. The next four peaks were split into two, because the peaks seemed to fluctuate from small to large, then small to large again.
So after drawing both the 3-nitrobenzaldehyde and 4-nitrobenzaldehyde molecules, we created prediction models for the NMR. When comparing the predicted NMR spectrum for each molecule, the one closest to the actual data was 3-nitrobenzaldehyde. The differences between the spectra was likely because of the contaminants in the testing, since the peak around 1.57 ppm didn't match any of the molecules' predicted spectra. However, the 1.57 ppm peak was possibly a remnant of the reactants, since the toluene reactants all had predicted NMR peaks around the 2 ppm. The shifts were also slightly different, likely as a result of the carbon ring. This caused a blending of the H signals. All in all, we are pretty certain that this molecule is 3-nitrobenzaldehyde.